June 4, 1996. The swampy air of French Guiana trembles under the weight of an approaching storm, and the roar of Europe's greatest engineering triumph. On the launch pad sits the Ariane 5, a colossal monument to human ambition. It represents 10 years of labor, $7 billion in development, and it carries a payload worth $500 million. The countdown reaches zero. The massive solid rocket boosters ignite. The machine rises flawlessly into the heavy equatorial sky, but exactly 39 seconds later, at an altitude of 2.5 miles, the rocket violently rips itself to pieces. It vaporizes its payload in a massive cloud of toxic fire. The initial assumption was mechanical failure, a ruptured fuel line, or perhaps sabotage. But when investigators sifted through the charred debris in the jungle, they found a truth that was much harder to swallow. The physical rocket was completely perfect. The explosion was triggered by a phantom, a single, dormant line of dead code that Europe refused to delete. To understand how a microscopic error could destroy a mountain of steel, you have to look back at the machine that came before it. By the late 1980s, the European Space Agency was dominating the commercial space race. Their workhorse was the Ariane 4. It was a masterpiece of reliability. It didn't just launch satellites. It secured Europe's monopoly on the sky. If a telecommunications company or a government wanted a satellite in orbit, the Ariane 4 was the safest bet on Earth. It was a machine that simply did not fail. But in the ruthless economy of spaceflight, reliability is never enough. You always have to go bigger. As the 1990s approached, the telecommunications boom was changing the world. Satellites were getting larger, they were getting heavier, and they were far more complex. The Ariane 4 was hitting a brutal physical wall. It simply didn't have the muscle to lift these massive new payloads into the stars. Europe was standing on the precipice of losing its crown. If they couldn't build a vehicle to carry the next generation of satellites, the Americans and the Russians would eagerly take their clients. The mandate was clear: build a new rocket, make it wider, make it stronger. Give it an acceleration curve that defies gravity with unprecedented violence. The answer was the Ariane 5, a towering titan of aerospace engineering. It featured a massive cryogenic core stage and 2 Titanic solid boosters. It was designed to carry not one, but 2 heavy satellites at the same time. The physics were groundbreaking. The metallurgy was flawless. But building a rocket of this magnitude is agonizingly expensive. So management made a decision. A decision that seemed completely logical at the time. They decided to save money on the invisible parts. To guarantee success, they mandated that the navigational software from the highly reliable Ariane 4 be copied and pasted directly into the brain of the Ariane 5. Why reinvent the wheel when the old wheel works perfectly? At the heart of this borrowed software was the inertial reference system. This was a highly sensitive computer that told the rocket exactly where it was in the sky. Before liftoff, this system ran an alignment protocol. It essentially calibrated the rocket's internal compass while it was sitting completely still on the launch pad. But here is the critical detail. This alignment protocol was completely useless once the rocket left the ground. It was only designed to work at an altitude of 0. Yet to prevent any launch delays caused by last-minute holds, engineers decided to let this useless alignment code keep running for 40 seconds after liftoff. Inside that code was a mathematical trap. The software was written in Ada, a strict programming language that forced computers to convert the rocket's horizontal speed into a smaller format. It took a massive, sprawling 64-bit number and tried to compress it into a tiny, compact 16-bit box. A 16-bit box has a hard mathematical ceiling. It can only hold a number up to 32,767. Anything higher and the box shatters. On the morning of Flight 501, the sky is clear. The countdown is methodical. At T0, the engines ignite with blinding fury. The Ariane 5 leaps from the pad. For the first 36 seconds, the flight is a triumph. The massive nozzles steer the craft with absolute precision. The physics hold. But the Ariane 5 is not the Ariane 4. It is faster. It is more aggressive. Its horizontal velocity is climbing at a rate the old software has never seen. Inside the flight computer, the useless alignment protocol is still running in the background. It is blindly calculating the rocket's accelerating speed, 36 seconds into the flight. The horizontal velocity exceeds 32,767. The 64-bit number tries to crush itself into the 16-bit box. The box breaks. The primary navigational computer detects an integer overflow. It instantly shuts down. Milliseconds earlier, the backup navigational computer encountered the exact same mathematical wall. It was running the exact same copied code. It too is already dead. The brain of the rocket is blind, but it doesn't fail quietly. As the computers die, they spit out a string of diagnostic error codes to the main flight computer. This is the system actually flying the rocket, but the main flight computer doesn't know the navigational systems are dead. It misinterprets this diagnostic error code as legitimate steering data. It looks at the string of numbers and concludes that the rocket has suddenly turned 90 degrees off course. The main computer issues an immediate, catastrophic correction. It orders the massive hydraulic nozzles to swivel to their absolute maximum limit. The rocket violently jerks sideways at immense speed. The aerodynamic forces are instantly fatal. The boosters snap off the main chassis. At 39 seconds, the automated self-destruct mechanism detects the disintegration. It triggers the explosives. $500 million of engineering is reduced to a rain of burning shrapnel. The aftermath of Flight 501 triggered one of the most intense forensic engineering investigations in history. The inquiry revealed a terrifying new truth to the aerospace industry. Hardware and software could no longer be treated as separate physical entities. You cannot strap old logic to new physics and expect the machine to survive. It forced a total revolution in systems engineering. It birthed the modern era of edge case testing, integrated simulations, and the strict, paranoid auditing of legacy code. We often think of technological failure in terms of physical weakness: a rusted bolt, a shattered pipe, a spark in the wrong place. But the Ariane 5 did not fail because its steel was weak, or because its engineers were unskilled. It failed because of an assumption. The assumption that the invisible logic of the past was safe to carry into the future. A machine capable of reaching the stars, brought down by a single, useless calculation. A microscopic ghost in the machine. A dead code that Europe refused to delete.